Hey guys, welcome to session 2 of METC 107. In this video, we're going to be talking about visualization and orthographic projection for technical drawings, or some people know it as multi-view drawing. Before we get to that, let's talk about what you should be working on at this point. Let's talk about schedule really quickly. So if we jump back at this point, hopefully, if you're taking this in the summer, remember we're doing 2 sessions a week. If you're taking it in the fall or spring, we're doing 1 session a week. So if you're doing this in the summer semester, you should probably still be working on maybe the welcome video, or hopefully have that done now. Make sure you've introduced yourself to the class, as well as our session 1 material, where we talked about the design process, what technical drawings are, and then you had a really quick assignment of doing quiz number 1. So if you're doing this in the summer, you should be kind of finishing that stuff up. Got a couple more days maybe. Remember, you have a week to get everything done. So if it's the summer semester, got a couple more days. If you're doing this in the fall or spring, you should have those things done now, hopefully, because you have 1 week to get everything done. So if we're meeting in the fall or spring, remember that you have 1 meeting a week instead of 2, like the summer people do. So if this is a fall or spring semester for you, the session 1 stuff should be done and turned in at this point, hopefully. So just kind of a heads up on schedule stuff. So let's get back to session 2. Let's talk about orthographic or multi-view drawing. What does this mean? So what we're going to be doing is we're going to be looking at a big fundamental piece of the language of technical drawing that we're going to use as engineers and designers, and that is what's called orthographic drawing. This becomes sort of like the standard setup for a drawing that everyone around the world will use to try and make this communication language the same. So we're going to look at a couple of geometric terms first, as we kind of eventually look at getting into our CAD software. We're going to talk about some different terms, and then we're going to talk a little bit about projection theory, which basically means, like, what are the different ways you can draw things? Artistically and technically, there are other ways of creating drawings of things besides what you see here, and we're going to look at those. Then we're going to focus in on just orthographic multi-view drawings and really get into the fine details of that, and then we're actually going to draw some together on paper. So we'll talk about that in a minute. But all the resources for this week, if you go into session 2 lecture resources, there's going to be some PDFs and handouts in there that you might want to print out. Or I'm going to do the sketching on my computer, actually. That way you guys don't have to try and watch me do this stuff on pencil paper. It's kind of tricky with a webcam. So I'm going to do mine on the screen actually here and record it for you. But you probably most likely will want to do yours with pencil. And so if you go to lecture resources, I have the PDF files for this week that you can download out of here, as well as the PowerPoint lecture that we're going through. So any of the handouts or drawing sheets that you see me using in the video are all available for you in session 2 lecture resources in Ivy Learn. You can get in there and download them. So you may want to pause really quick, get those, print them out, and you'll be good to go. So let's talk about some terms here, geometric terms. These are things that you're going to need to know very, very well once we get into actually using our CAD software, probably session 3. If I go back and check really quick here, I think in session 3 we start to actually get into Inventor software. Yeah, so really this is our last lecture of talking about traditional technical drawing techniques. Next time we're actually going to look at using the Autodesk Inventor software. So a quick friendly reminder, if you have not downloaded that already, go to the Home tab in Ivy Learn and hit the free Autodesk Inventor download button. Okay. There may be a requirement also for you guys to verify that you're a student. I've had a couple people contact me about that already. Autodesk has started trying to check whether or not people are actually college students or high school students. So what you need to do in that case, if they ask you for additional documentation or additional verification, just go into My Ivy, and you're going to print out a copy of your student schedule, and then take that like as a PDF file or a JPEG or whatever works for you. Take that and upload it to Autodesk if they ask. Typically, just showing them a copy of your class schedule will get the job done. There is a 14-day time limit on that once they ask for it, so make sure that you do it ASAP. I accidentally forgot one time and locked myself out, and it is a pain to get access back to that if you let that timer expire. So just a heads up, next session we're going to start looking at the Inventor software. Make sure you have it downloaded. If they ask for verification, go to MyIvy, print out a copy of your schedule as like a PDF or a JPEG, or screen capture it, take that and upload it to the Inventor website or to the Autodesk website. And I think usually within a day they'll give you access. So just a heads up, go ahead and get that done now if you can. All right, so back to session 2. These are terms you're going to need to know once we get into the CAD software in session 3. And the reason is we're going to be doing something called parametric sketching. And parametric sketching requires you to be very good at geometric relationships between objects. So for instance, saying like there's a right angle between these two lines. You have to understand this terminology. What is an acute angle? What is an obtuse angle? Okay, so remember, a right angle is 90 degrees exactly, an acute is less than 90, and an obtuse is more than 90. Corny joke for you. My triangle family here, they say, we obviously have the nagging wife here and the browbeaten husband. And the wife says, "Ha! You wouldn't know an isosceles if it bit you in the hypotenuse. Really, Frank. Sometimes you're so obtuse." And apathetic Frank says, "And you're always right, Vivian." My little triangle down here playing on the carpet with its toy triangles. Anyway, stupid joke. So back to our geometric terms. These are also important. So complementary and supplementary angles. Okay. Complementary basically means that if you take these and you add them together, they add up to 90. Supplementary, if you add them together, remember that they make, instead of a right angle like complementary, supplementary angles add up to make a straight line. I always remembered that because supplementary and straight both start with S. So supplementary angles make a straight line of 180 degrees. Okay. Then we also have opposite angles. And this can be handy when you're doing CAD sketching, knowing that opposite angles are equal, or in math class we say opposite angles are congruent. Basically meaning if I have two straight lines and they cross somewhere, the angles on opposite sides of those lines are equal to each other. Okay, so hopefully that stuff is kind of review from your math class. Now we're going to get into a couple of weirder ones that you might not talk about necessarily in math class as much, but you're definitely going to be using them in our CAD software in session 3. So you've probably talked about tangency in your math class before, especially if you've taken like pre-calculus or trigonometry, a math class that's very heavy in graphing, maybe even in some of your algebra classes. But tangency, if you remember, is the description of two objects that approach each other and touch at one infinitely small point and then diverge again. So here are some different examples of applications of tangency. So you can have tangency between a line and a circle, two different ways, right? So I could have that line that is tangent at one infinitely small point to the circle and then passes on, or it could stop at that point. Okay, so both of these are examples of tangency. One that's kind of lesser known is the tangency between two circles. So I can have two circles of different sizes like this, and those two circles touch, their circumference touches at one infinitely small point, which would be, approximately here. So these are examples of tangency, and knowing that all three of these exist will make you a much better CAD modeler once we get into our CAD software. So just keep these in the back of your mind. Tangency doesn't just have to be a line in a circle, and it doesn't always have to extend through like you might see in math class. Okay, these are both also examples of tangency. You can also have tangency between lines and arcs. So, I could have maybe something like this where I have a line that approaches and I have a curve, and then I have another line over here that's also tangent to the same curve. And maybe the bottom part of this circle down here is trimmed off. So you can have tangency between any curve and any line, basically, or the possibility for it. A couple other terms, parallel and perpendicular. Hopefully you're familiar with these. Perpendicular just meaning that we have a right angle there. Parallel meaning that these two lines go forever in every direction, or go forever in both directions and never cross. They never get any closer and they never get any farther away from each other. So those two lines are parallel. Now here's some weird ones that you probably have not heard about before, at least most people haven't, because these aren't really heavily used in your math class, but for CAD software, these are must-know terminology, okay? So commit these to memory. Coincident and collinear. Let's talk about the easier one first, which is collinear. Collinear basically means that I have two lines and they lie in line with each other, but they don't touch necessarily. They can, but not necessarily have to. And all that means when I say something's collinear, that basically means if I extend one of these lines, it's going to overlap the other one. Okay, they are collinear or lined up or in line with one another. Now, kind of the other similar version of that is something called coincident. Coincident really talks about endpoints or center points. So in this particular example, we have two lines that are coincident with each other. I have this line, and we're talking about the endpoint on it right here. That is coincident with this line and the endpoint on it. So if I take those two lines and I make the endpoints of them coincident, right here, noted by my red circle, so I can take those two lines and make them coincident right here. What that means is that those two endpoints on those two different lines match up with each other perfectly in XY or 2D space. Okay? So in other words, the endpoints of those two lines are locked together. That's one example of a coincident relationship. The other way you could do this maybe would be instead you might have, let me go over to my sketching here really quick. Let's sketch something. You could have a circle, for instance. I'm going to draw a really bad circle. Whoops, that's my eraser. Let's get the paintbrush. I could have a circle, for instance. That's not too bad. And its center point is approximately here. And I could have a line also that I could say is coincident with the circle, with the center point. Now, this is a little bit weird. This is a lesser known one that causes people a lot of trouble in CAD software because they don't know you can do this. So I'm going to try and tell you guys about it early on. I've taught this class enough times that I know that this is one of the constraints or geometric relationships in math and CAD modeling that give people tricks because they don't know it exists or they don't know you can use coincidence this way. Okay, so what this means, if I take this line, if it's coincident with the center point of this circle, what that means is if I was to extend this line, it would have what we call an apparent intersection with the center point of this circle. And all that fanciness means is that if I extend this line, it's going to go through the middle of the circle. Okay? But the way a CAD modeler would say that is they would say this line is coincident with the center point of this circle. And there's a specific way they would describe that. Okay? Now, you can also do it where it actually goes through and connects. So we could do that, right? Assume my line is straight here and my circle is perfectly circular. But that's an example of being coincident also. In that case, I would say the end point of this line is coincident with the center of the circle, okay? And you could extend it through and they would connect. So when we get into our CAD software, it's going to be all about these relationships between shapes, between lines, arcs, circles, rectangles, different shapes. How do we relate them to one another? Parametrically. So understanding these terms now is going to be paramount next time to actually starting to do something of value when we get into our CAD software, Autodesk Inventor. Okay, so moving on. A couple other terms. Concentricity basically means if I have two things that are round, they share a center point. They're concentric with one another. Okay, I can also have eccentricity. So eccentricity would mean that I have two round things and they are off-center with one another. They do not share a center point. Okay, so I've got these engine pieces laying all over my garage because I've shown you guys in the past I'm working on the engine in my MR2. So here, hopefully you guys can see this. This is a cam gear for a camshaft where your timing belt goes. So there are some examples on here of eccentricity and concentricity. So if you look at this, I've got the overall shape of the cam gear is concentric with the hole in the middle. If I can imagine the overall outside of this shape, or maybe even like this inner section right here, that is concentric with the hole in the middle where the bolt goes. Okay, that's an example of things being concentric. I also have eccentricity all over this thing. You can see these holes they've put in here to save weight and save material are eccentric with the overall shape of the cam gear. So the center of the overall cam gear is right here in the middle, right? The center for each one of these circles is in a different spot. So this part's kind of unique because it has concentricity and eccentricity on the same piece. But that's an example of a real life piece where you might see these shapes come to life. Okay. Moving on, we can also talk about polygons. So this doesn't have to just be a hexagon like you see right here. It could be an octagon, pentagon, even a rectangle maybe. So you can inscribe a polygon or circumscribe it. Okay. The way I always get these confused, but the way I remember this is inscribed, the polygon is inside the circle. You'll use this a lot, like if you're drawing fasteners, like nuts and bolts. This trick is really, really handy if you're doing like a 6-sided hex head bolt, for instance. But you can inscribe a polygon inside a circle or circumscribe it. So when you inscribe it, notice that the corners of the polygon hit the circle. And if you circumscribe it, the flats on the polygon will hit the circumference of the circle. Okay, so those are two other terms. Then our very last one here, talking about geometric terms, radius and diameter. These are really not necessarily relationships between two things, but this is a measurement of arcs or circles. And I'll tell you now, there's kind of a rule of thumb that CAD designers use. If you have something that's less than a circle, like a partial curve, you dimension that with a radius. Okay, so if you have part of a curve or like half of a circle or a fourth of a circle, dimension that with a radius dimension, which remember is the dimension from the center of the circle to the edge or to the circumference, okay, or to the arc. If you have a complete circle, the rule in technical drawing is that you dimension that with a diameter. Diameter, remember, being the measurement all the way across the circle passing through the center point. Okay, so radius for partial curves, diameter for complete circles. We can also talk about things being coaxial. And this is kind of our final one. Think about this sort of as, this is sort of like the 3D version of collinear. So we talked about lines being collinear, right? Back here. So we talked about two collinear lines line up or they're in line with each other. Coaxial is just the 3D version of that. So imagine, you know, I've got two cylindrical objects and they share a center line axis. That means they're going to line up. Okay. Or for instance, if I come back here, let's grab something in my toolbox. You know, if I line these things up, you know, if I've got two cylinders, this is not coaxial, obviously, but if I line these up and make their center points match up, now I've got this object that's coaxial. I've got two different shapes of cylinders, two different sizes, but they share a center line axis in 3D between those two shapes. So think of coaxial as the 3D version of collinear, okay? And I have to say this is incredibly handy being at home in my garage. I can grab all kinds of junk that I have lying around for examples. I'm kind of getting addicted to this. So, okay, so let's move on. Let's talk about projection theory. What are the different ways you're capable of drawing something as a person? And why did we decide to do it one specific way for technical drawing as engineers? And why not the other way? So there's two different kind of categories of drawing that humans use. One is called perspective projection, and the other is called parallel projection, okay? And it all has to do with depth perception and the sizes of objects relating to their depth versus their actual size. So for instance, if we look at a perspective projection drawing up here, this rectangle right here is intended to be your piece of paper. The blue rectangle in the middle is the drawing, and what they are drawing is this object in the back. So imagine, for instance, you know, I've got a piece of paper. Your station point is your eye. So imagine, you know, my eye is looking at that thing, and here's my piece of paper that I'm drawing on. And in the back, I've got this object that I'm looking at, right? I'm looking at drawing this thing. That is kind of what we're looking at in these two diagrams. But the way we draw it is different. And you can tell because if you look at those two drawings, one is bigger than the other. So why? Well, it's because one is an example, the top one is an example of perspective projection, and the bottom one is an example of parallel projection. The difference between them, you'll notice, is that one is true size or 1-to-1 scale, the other one is not. So if you look at parallel projection, it is 1-to-1 scale with the object in real life, meaning that if it gets farther away, the size is not going to change. Compared to perspective projection, we take into account depth perception. And what that means is as that object gets farther away or closer, its size will change. If it gets farther away, it's going to get smaller. If it gets closer to you, it's going to get bigger. Now, a lot of people would say, well, that's more accurate to real life. Why don't we just do that all the time? Because in real life, we know if things are closer, they're bigger, and if they're farther away, they're smaller. So why would we lie about that on our drawing when we create technical drawings? The reason has to do with scalability. If I take a drawing and I want to measure a dimension off of it, I can't in perspective projection because the depth perception will cause my measurements to be increased or decreased by an unknown amount. And what that means is if I have a scale or a ruler and I want to measure that drawing, I can measure it, but the measurements are meaningless. I have no way to ratio those to the actual size of the real life object. Okay? In parallel projection, since we discount depth perception and we throw it away, your drawing in a parallel projection environment, like the bottom one down here, what we use as engineers, is always perfectly scalable. We might scale the entire drawing up or down by a ratio, but if I take a measurement off of my drawing, I know that I can always scale it in some way back to the original object. Okay? So is perspective better than parallel, or is parallel better than perspective? Not necessarily. They just have their own advantages and disadvantages. So in a nutshell, perspective projection drawings look more realistic, but you can't measure them. Parallel projection drawings do not look as realistic, but they are fully scalable and measurable, and that's why we use them. Okay, so if you want to get into even more, get into the weeds even more on this idea, you can take these two categories and break them down even further into subsets. Perspective drawings can be 1-point, 2-point, or 3-point perspectives. We're not going to use perspective drawings in this class. It's really more of an art class thing, but I'll show you examples. Excuse me. We're going to look at parallel projection exclusively. So there are different categories of parallel projection drawing also. I'll show you an example of some of them. But the two types of drawings that we're going to use in this class out of this whole chart are first angle orthographic projection drawings, which we're going to talk about today, and then isometric drawings, if I can highlight it up here. My computer's being stubborn. There we go. Isometric drawings. So the two with the stars on them are the ones we're going to use and the ones that historically get used on a technical drawing. So let's look up a multi-view drawing really quick here, just so you can see an example. So something really basic. Here we go. So super basic drawing starting out here. But if you look at this, here are your two types of parallel projection drawings that we're going to use. So we're in that red category now. So here are your multi-view, your first angle multi-view drawings, all three of them, they go together. And then up in the corner, here's your isometric view. Now, why do we have these different views? Let's talk about this very early on so we know why we're packaging the drawings this way when we do them in a multi-view drawing environment. The views down here are really the most important ones. These are the ones where you show all of the small, tiny details. You totally describe the object. You show all your different line types. You fully create all of the geometry and all of the measurements down here of every face of that object. So as far as providing information to the viewer, this is where most of it happens. This is where all the dimensions are going to be, all the notes. Like if we're going to drill a hole through it, for instance, this part doesn't have that, but if we were going to drill a hole through it, we call out all the infinitely small details about how that hole is to be drilled. Okay, so what is the isometric view for then? Well, this one is really what we call a pictorial view. It just helps somebody visualize what this thing means. So imagine for a second if I gave you this drawing, but I took this view in the corner, I completely took it away. It becomes very difficult at that point for the human brain to package these together and figure out what this would look like. So going from isometric to multi-view and from multi-view back to isometric, that's called interpreting a view. So you'll get better and better at that as you look at more and more technical drawings, but that's the trick, is can you go back and forth in your mind between these two? So for instance, when I look at this view down here, this front view, can I see in my brain how that really is looking at this object this way? Or if I look at the right side view over here, I'm looking at the object this way. And that's the trick. Can you take these three views and interpret them or stitch them together in your mind, and in your mind see this object? That's what we're trying to do in this class, is really train you to be able to go back and forth between those two things. And not just that, but create your own designs where you can do that as well. And then ultimately put it on paper so you can communicate that idea, or not even on paper, but just put it in a fundamental format where you can share it with somebody else. Okay, so that's an example of an isometric view and a first angle orthographic view. So let's compare really quickly for kind of one last thing here about projection theory, comparing perspective and parallel projection one more time. So here's kind of a direct comparison. And you could Google tons of these. If you look up perspective versus parallel projection, if you Google it, you're going to find all kinds of examples. So here's perspective projection, a drawing of a stapler, versus parallel projection. Notice in a parallel projection drawing, as you go towards the back of the drawing, things do not get smaller. Okay, they stay roughly the same size, and you can tell by like looking at the base of this stapler, it is not going to shrink down and get smaller like the one on the top does. You can notice it's a little bit thicker here, and as you go farther away from it, it tapers down to what we call a vanishing point here in the background. So if I extended these lines far enough, they are not parallel. They're eventually going to converge at a vanishing point way up here. Okay, parallel projection gets its name because edges or lines that are parallel in real life are parallel in your drawing. So if I took, for instance, this edge and the bottom edge of this stapler in the parallel projection drawing and I extended them forever, they're parallel. They're never going to touch, hence the name parallel projection. Okay, so there's just kind of a direct comparison. Perspective projection is more visually appealing, but it's less useful. So here's some quick examples of one-point perspectives. Again, these are more artistic. They're used for like art and photography. They're very realistic looking, but they're not very useful for building things. So these are examples of one-point perspective because they all have a single vanishing point. So you can see in each of these, there's one point where everything pinches down towards, and that is what we call the vanishing point. Okay, so one-point perspective photographs. You can also have two-point perspectives. So typically you'll see these when you're looking at the corner of something. So for instance, like in this drawing, this is probably the most obvious. You can see I have two vanishing points in this architectural rendering. We have one over here and one over here. And so the top and bottom of this building in the drawing taper down to those 2 points. In real life, we know that's not going to happen, right? That the edges of that building are not sloped down and they don't disappear. But when we look at that, it mimics the way our eyes see things, and so it looks very realistic to us. Here are other examples like photographs of two-point perspectives, but they're 2 points because there's two vanishing points, okay? Usually off to the sides. We can also do a three-point perspective. These are a little bit harder to identify sometimes. You can see up here, the reason they're harder to identify is because those three vanishing points typically are very far away from each other. So now you have a height vanishing point and both like a width and length vanishing point. So things are tapering down in three directions now. So the same left and right, and then you would also have a vanishing point up at the top. You typically see these like in photography or art if you're looking down at something or looking up at something. So looking now at the other category, so switching gears, now we're talking about parallel projection. So we're done with the artistic perspective projection. We can leave that behind now. Hopefully you know what it is at least. But now we're going to go into our parallel projection category, and we're going to talk about axonometric drawings. So this category here, remember out of this category, the one we're going to use is what's called an isometric drawing. But I want to show you a picture at least of a dimetric or trimetric drawing so you can see what those are and maybe why we decided not to use them. Okay, so here is an example of the three, all drawn the same object for comparison purposes. And it has to do, when you draw these, it has to do with the angle between the axes. So for an axonometric drawing, you can see for an isometric drawing, isometric means one measure or one angle. So what that means is each of these, they're all 120 degrees. And what it does is it breaks up your X, Y, and Z axis in your drawing equally, and it gives us the best overall view of what this looks like. For a dimetric drawing, it's the same thing, it's just rotated slightly. So for a dimetric drawing, two angles are equal. So in this case, you can see angles A and C are equal and B is different. So we've taken that drawing and we've just rotated it slightly. And then if you take it and you rotate it again another direction, you get what's called a trimetric, where none of the angles are the same. So you've just basically rotated it to some arbitrary configuration. And so that's what it would look like. That's called a trimetric view. So all of these are axonometric views, but the one we decided to use as engineers is the isometric. Okay. So here are just some examples of other isometric drawings so you can see them. Why do we use these? They're just for visualization purposes. if you have a really complicated object, showing somebody the isometric for it can make it much easier to understand. So that's why we throw them onto the drawing, usually in the top right corner, just for visualization purposes. Do not do this like they have done here. It's actually considered bad practice to dimension these isometric drawings. So don't put dimensions on isometric drawings. It's really considered bad practice. Then our very last category here, if we go up and kind of look back at our chart again, we can talk about oblique drawings. We will not use these at all, but I want you to see why we picked axonometric drawings for our technique as opposed to oblique drawings. So these are still parallel projection drawings, but we don't use them because they don't look very good. So going down, just to show you a couple of oblique drawings, these are scalable typically, but they don't look realistic. So you can see now, instead of looking at the corner of something like we would do in an axonometric drawing, we're looking at a face. So we've really sort of rotated it 45 degrees roughly. But when you look at a cavalier or a cabinet oblique drawing, they typically look very fake, especially cavalier drawings. So what this means is it's drawn full scale in all three directions. So this is a cube drawn in cavalier oblique drawing style. So if you measure this with a ruler, it's 24 by 24 by 24, except it looks really weird when you do this, and it is misleading. So here are some examples of orthographic drawings. So let's talk specifically about what is an orthographic drawing. Well, an orthographic drawing is nothing more than we take an object and we break it down into all of its possible faces. And there are 6 possible orthographic views, and we choose a few of them typically to put onto a drawing page depending on what we're trying to show the viewer. So this is something that's very near and dear to my heart. I grew up with one of these. So this is an old Nintendo 64 controller. Some of you may recognize this depending upon your age. If you're a really, really old millennial like me, or maybe a younger millennial, you might recognize these things. But so what have they done here? They've made an orthographic drawing of this object. So why do this? Well, it really kind of shows you maybe what's hiding in some views that you can't see. So if you look at the front of the controller, there's things you can see that you can't see in the back and vice versa. So one of the things that was always kind of weird about this controller was it had this button on the back, and that was kind of the first time that anyone had done this in video gaming. Like, let's take a button and put it on the back of the controller where your hand goes. The other thing that was kind of weird is you had this little card slot on the back where you could plug these memory cards in to save your game progress. Now, when you look at the front view of this thing, you can't see that stuff back there. It's not until you do an additional orthographic view of the back of the object that you can see, oh, well, hey, there's some more going on back here, right? We've got this slot right here where you can put cards in. We've got another button. We've got a bunch of screws that hold this thing together. You can see the contour of the shape of the controller a little bit better. And same thing like with the top and bottom views, right? You can see in the top view, well, hey, there's some more buttons up here, and here's where the cord connects. And I can see those holes down there for those plastic screws that go in there. So by putting these views together, we can completely describe this object a little bit better to somebody that may not know anything about it. So, you can do this with other objects also. So like, for instance, here's an Audi. You can see the same thing there. We can do these multi-view drawings for a car also and try to describe it a little bit better. So why do we do this? Okay, why take these objects and try to completely describe all the faces of them? Well, it's because we're stuck working traditionally in a 2D system, right? Even though we have computers now, a lot of times we're stuck working on a flat screen still. So most of what we do is still a 2D environment. We can share 3D models with people, but for the most part, the world still works in a 2D format, whether it's a screen like a television screen or a tablet or a phone, or even a piece of paper. These are all 2D systems, right? So we have to have a way of describing 3-dimensional objects on a flat 2D system. And the way we came up with doing that is orthographic projection, okay? Now, everything we're going to do in our CAD system is defined by the Cartesian coordinate system. Now, if you've taken a math class where you talk about graphing things, you're probably familiar with the Cartesian coordinate system that was developed by René Descartes, the French mathematician. We kind of credit this to him. And unfortunately, he sort of got depressed later in life, and he felt like his contributions to math were meaningless. It's unfortunate that he couldn't see today all of the things that came about because of his coordinate system. Basically all of manufacturing and engineering is dependent upon the Cartesian coordinate system, along with most of mathematics. There's all kinds of things that we use on a daily basis that are dependent upon grid systems and graphing. And without the Cartesian coordinate system, none of that would exist. So CAD software is no different. Everything that we draw is created on a Cartesian coordinate system in the background. Now, we're not going to do it with equations typically like you would do in math class. We're going to draw a little bit more free, like you would use almost like a pencil. But behind everything we create, that mathematics background is in the back, making it work and making it function and causing it to be the right size. So we can thank Rene Descartes for our coordinate system that we're utilizing. So we're stuck working in that flat 2D system most of the time, or at least transmitting information that way. When we create our CAD models, we're going to be working in 3D, right? We can actually 3D and add that Z axis into what we're doing. But the trick is if we want to share that design with somebody else. So unless you want to give someone your original file for whatever you've designed in your CAD software, there's really no good way to try and describe that object to them in 3D. So eventually at some point you're going to have to pass through a 2D filter that's going to strip information out of your project probably. And that's why we came up with multi-view drawing. Okay? How do you describe a 3D object and break it down to work in a 2D world? So why do we do this? Let's talk about, what do you get when you make a multi-view drawing, or why did we structure it the way that we structured it? So let's look at some examples here. Every drawing view in a multi-view drawing is going to show two axes. Okay, so if you look at this house, for instance, we've got our isometric view up here in the corner. But if I do multi-views of it, you can see if I look at the front of the house, I can see two dimensions. I can see width and height, but I can't see the depth. I don't know how long the house is. If I go to the top view, now I can see that depth and I can see the width. But now I don't know how tall the house is. I don't know if it's a 1-story house or 2 stories. Now if I look at the right side view, I can see I can see 2 dimensions, but they're different. I can see height and depth. Same thing over here, height and depth. So in every view, you get 2 dimensions, but if I take them and I stitch them all together, you have all 3, okay? So here you have width and height, here you have width and depth, and here you have height and depth. But if you put them together, you get the full object there, okay? So this is how we learned as humans to take objects and break them down and describe them in 2D drawings. Now, when you do a multi-view drawing, there are 6 possible views you can do. So you can do front, back, top, bottom, left, and right. Think of it like a cardboard box, right? If you have a cardboard box and you take it and you cut it apart and fold it flat, there's 6 panels or 6 faces. Some of these have nicknames that you can see here. But when we do a drawing, there are 3 views that are the most common that we're going to use. So if you look at this, most of the time we're going to use the front view, the right view, and the top view, okay? So why do we throw out the left, back, and bottom view? So if you take a second and look at this, see if you can figure out why, as I get a drink here. So the reason is that these things become repetitive. So if you look at the left view and the right view, they're pretty similar, right? They really don't provide any extra information. Same thing with the back view and the front view. They're nearly identical, as are the top and bottom views. So it's not that it's wrong to put these other 3 views on there. It's just most of the time we trim them out because we've decided we really don't have to have them to fully describe the object, okay? So here's just another explanation of kind of what I told you before about which views cause you to see which dimensions. So think about this as if you're standing or flying or looking at this object from different orientations. Each one of these orientations is going to show you a different view. So front and back views show X and Y. Top and bottom views show X and Z. And left and right views show Z and Y. Okay. Another thing that might help you is this thing called the glass box method. This helps people visualize how these drawings are created sometimes. So let's see if I can show you guys this quick little animation here. And you can click on this also in the PowerPoint and go check this out. Let's remove this awful cheesy music here. There we go. So if we kind of skip ahead here. All right, so we've got this object, and they're just going to sort of help you visualize this. They take this thing and they fold it up into a cardboard box, or in this case, what they call the glass box. So we're going to draw this object, take it and completely enclose it, all 6 sides. Then what you do is you highlight the faces and decide which ones you're going to draw on which faces of the box. And you take them and you project them outward until they hit the face of the box, and that becomes the drawing. So what you're doing at that point is you're picking up any of the faces or edges that you can see. There are also some things you can't see. Okay, like this hole in the middle, for instance, you can't see in some of the views. Those are noted by dashed lines. So for instance, at our front view, you know that hole is in there, but it's noted by this dashed line because you can't necessarily see it in that configuration. But if we take this box and we cut it apart and open it up, that becomes your multi-view drawing. Okay, so there you go. That's your 6-view multi-view drawing. And most of the time we would trim off these 3 and that becomes our drawing. Front, right, and top is pretty much all you need. But you'll hear people talk sometimes about glass box method or the glass box theory. That's all they're talking about. It's just a drawing method. Okay. So when we draw something, there's a couple things you need to know as a designer. How do we pick the front view for an object? So, you know, I've shown you this thing a bunch of times. If I'm going to draw this, how do I decide when I draw it? What do I want to be the front view? And there are 5 rules of thumb you can use to try and determine this. So the first is you want to show the longest or the biggest dimension in your front view. Okay. So the longest dimension in this piece would be from here to here. So I want to make sure that that is visible somehow. Now in this particular object, this one's kind of weird because you can't eliminate that. I can see it in this orientation, or like this. Okay, whatever way I rotate this thing, you can always see that dimension. So number 1, I really can't mess up for this piece. 2, the least number of hidden lines, or that kind of goes along with 3, the most descriptive. Okay, so in this case, if I show it like this, that's no good because I can't see all those individual holes that are drilled inside there now. So we know now, based on rules 2 and 3, we want some kind of configuration like this, right? Now numbers 4 and 5, what is the most natural position and the most stable position? So to make this final determination, if I was going to draw this, probably what I would do is I want the face that would be sticking out when it's mounted on the engine. I want that to be my front view, which would be this way. And then as far as rotating it, I'm going to put it maybe in its most natural orientation, or what a mechanic would call top dead center on the engine. That basically means where is this thing going to be rotated at when the engine is at the beginning of its firing cycle. So in this case, that's noted. You guys may not be able to see this, but there's a little, like a pin up here at the top on this thing. So if I was going to draw this, out of all the different configurations and rotations I can do to this, I'm going to make sure that I mount it with the correct face out. That's going to become my front view because that's how it's going to be mounted on the engine. And then to try and decide what is up, I'm going to put that locating pin at the top in my drawing. So I would draw this thing like that. Okay, that meets all 5 of my rules. I can see the biggest dimension. I have the least number of hidden lines because I can see all this stuff on the inside. Okay, it's the most descriptive, the most natural, most stable. If I find something else here really quick, let's see what else I can dig up. About this crazy thing. So this is a puller for axles. You can use it to work on like CV axles on a front wheel drive car. So how do I decide what view I want to do for this thing if I'm going to draw this on a technical drawing? Okay, so rule 1, we got to see the longest dimension. So the longest dimension on this thing is clearly from here to here, right? So we need to see that somehow. If I draw it like this, that's no good, right? Because I can't see that long dimension. So I know my drawing needs to show this dimension in the front view somehow, you know, regardless of how I rotate it. I want the least number of hidden lines. So what that means is I don't want to draw it like this. I can see the longest dimension there, but I have all these lines that are going to become hidden, all these holes that are obscured when I draw it like this, okay? So rule number 1 tells me it needs to be some kind of configuration like this. Rule 2 tells me that it needs to be, you know, either like this, or this, or this, or this, right? I got 4 choices basically now. Now I'm down to what is the most descriptive and the most natural position. So if I'm looking at other things on here, well, what would most people say is up on this part, or what's the most natural? Well, probably either like this or this, right? It doesn't make much sense to turn it like this because that's not really how the tool gets used. So now I'm down to, do I want to draw it like this or this? And kind of to make my determining factor here, I've got a couple bolts that go in down here at the bottom. I would like to see those in my drawing. So I'm going to make sure when I rotate this that those 2 bolts are visible. So for this thing to meet all 5 of the rules, I'm going to draw it like that, okay? In that exact configuration. That's going to be my front view. This would become my top view. And over here for you guys would become the right view, okay? So front, top, right. And I hope recording this, I don't know, we'll see. I hope when I record this and run it through the video software and everything that this is actually right for you guys, but I have a feeling maybe it's not. I don't know. It should be anyway if you were actually sitting over there. But this visualization stuff gets kind of complicated sometimes. So what about for this thing up here? What would you pick? So take a second and look at it. What's going to be your right view? If you're cheating, you can probably look down here and see the finished drawing. So they're determining that this front face right here, this is the front view. And then from there, you can see all the other views that come off of that. So kind of wrapping up here, a couple other things that we need to talk about. And then we're going to get into actually drawing some of these things. So this is getting a little long. I'm going to see just what's absolutely important here that we need to talk about, because I want to spend some time actually drawing some of these things together. So looking at this, we're not going to draw these by hand, so I don't think we need to worry about that too much, or at least not a lot of them. This is things you need to know. If you remember from our chart up at the top, there's 2 types of orthographic projection. There's first angle and third angle, okay? Now, this is where people can get into an argument, and something people are really, really good at. We're all good at arguing, it seems like these days. What is the difference between these? Okay, so this is the one thing I think we got correct that the metric system got wrong. It's like the absolute one thing. We screwed up everything else. The metric system is superior in every possible way, and every country that uses the metric system is light years ahead of us as far as science and technology and measurement go. Okay, or at least the system they're using. The metric system is superior to the US customary system in absolutely every way, in my opinion, except this. This is where we got it right, is creating technical drawings. So we do, and Australia does, what's called third angle projection. What that means is that our drawing plane is between the object and the viewer, meaning that if we're drawing this thing, my paper or my drawing plane is between my line of sight, or between my viewing point and the object. So we draw like this. The rest of the world does first angle projection, where you flip-flop them, and they do this. And you really can't tell a difference. All the same information ends up on the drawing, except when you look at the finished drawing, it causes things to flip. So if you look at it, what you end up with in a third angle projection drawing like we do and like you would see in Australia, here's the front view, the right view, and the top view. And the thing that makes first angle projection inferior, in my opinion, is if you look at this, here is the front view, the top view, and the right view. And what I think is so stupid about this is the right view is on the left side of the drawing and the top view is on the bottom of the drawing, and it makes no sense to me. I had a student one time that was working, I think is doing an internship, and he brought in a drawing to me, and he said, "Hey, look at this drawing we got at work. Somebody sent this to us. We were making fun of it at work, and we're getting ready to, we're going to contact the company that sent it to us today. They're one of our subcontractors, and we're going to ask them to please fix the drawing and send it back to us." And he had told me about where he worked, and I said, "Well, hang on just a second. Like, this subcontractor you guys are working with, I know you guys have a pretty big company. Where are they from?" And he said, "Oh, it's some German company. They don't know what they're doing." I thought, whoa. They actually do know what they're doing. Before you guys send them an email and call them out on their drawing techniques and look stupid, here's what's going on. And so I had to explain to him that they're doing first angle projection. You're in the United States, so you're used to third angle projection, and you guys are going to get into this back and forth match where you both try to tell each other you're wrong, and technically you're both right. So If you ever receive a drawing from someplace else in the world, you probably will see that their views are switched because they're doing first angle projection instead of third angle projection. Are they wrong? No. Is third angle projection a little bit superior? I think so, just because it makes more sense to me. But someone that has done first angle projection their whole life, that's the language they speak. And if you try to convince them to do this, it's going to be totally backwards to them. Same thing for me. When I see a first angle projection drawing, it just blows my mind. Like, whoa, wait a minute, what are you doing? Why is the right view on the left side? And so it's really just what you're used to and what country are you from and what is the standard there, okay? Another thing we need to talk about really quickly is alphabet of lines. On a technical drawing, you're going to see different line styles or line types that get used for different purposes. So the three we're going to use today are the three most common. We're going to look at visible lines, hidden lines, and center lines. And as we practice some drawings, you'll see those get used a little bit more. Okay. So kind of wrapping up here, I've got a little brain teaser for you, and then we're going to look at precedence of lines, and then we're going to draw some drawings. So get your pencil ready. So here is a quick brain teaser for you. This bus is going one way. How do you know? Okay, so the answer here you can see obviously is it's going to Los Angeles, but there's a reason. So I usually show this to my classes and I ask them, okay, this bus is traveling across the country. It's going on a one-way trip. Is it starting in Los Angeles and going to New York, or is it starting in New York and going to Los Angeles? And there's a way you can tell by looking at the picture. What is it? And I get all kinds of crazy answers. I'll hear people say like, well, it's the windows, right? I can see the lines in the windows, and if the sun is up here, then it's shining down on the windows, and that means that if the sun is over here and the building's in the background, and I've had even people tell me what skyline they think this looks like in the back, or, you know, where did the road go? Why are they driving through dirt? And that's a good question. So looking at this picture, can you figure out why the bus is going to LA? Here's the trick. The trick is not what you can see, it's what you can't see. Okay, where are the doors? So there are no doors to get on the bus. So since the bus is in the United States and we drive on the right side of the road, at least most of the time, if you drive on the right side of the road, the doors for the bus have to be on the right side so that it can pull up to the sidewalk and people can get in and out. So if you can't see the doors to the bus in this configuration, that means they're on the other side of the bus, which means the driver is going to be up here and the bus is going to be going left or west to LA. So why do I show that? Well, it has to do with line types. Okay, so remember in some of these views, we talk about hidden lines. And the reason is sometimes in a drawing, what you can't see is just as important or passes along just as much information as the things you can. So take this thing, for example. The hole that goes through the middle, you can only see in one view. But if I can show that in the other two views, it provides extra information to somebody that they wouldn't normally see. Or, you know, some other examples like this. Look at all the hidden lines in these drawings and look at how much additional information that passes along to the viewer. If you take those out, you're basically withholding information, and it makes your objects very difficult for people to understand. So these line types are important because they allow us to share information with people in a most easily understood format. The trick is that as we have these different line types we're trying to balance, sometimes they want to overlap with each other. And we're going to see some examples of that as we go through and try to draw some of these. But here's how you decide what to show or what to leave off. If you can remember this order of importance, when you draw things, visible, hidden, and center, you already know what to do. So let's look at 3 examples up here. Okay, so remember, visible, hidden, and center. So I'm going to take this and increase the size a little bit here. And just for kicks, let's take this out. Oops. Okay, so here's our drawing. Hopefully you guys can see that better. So if we look at example A right here, what's overlapping? Well, we've got this edge right here, right? That's showing this edge in the top of the part. And that is overlapping with the center line for the circle. So there should be, you know, kind of like this. For instance, if you look at this drawing, you can see the center line that goes through the whole of this. Or over here, you've got a center line, or down here. anytime you have a hole or a round object, you should have a center line that goes through the middle of it. And you can see that on all these different drawings. So why did they leave it off here, right? Because we know we have a hole right here, so shouldn't they have a center line here? The reason they left it off is because it fights for position with the line on top. So how do you decide what to show? Well, you just have to remember the order of importance: visible, hidden, center. You can remember that, you know which one to show. So at the top, we show the visible line because it's the visible one, it's the most important. Leave off the center line. If we look at B, what's going on there? Well, we have this edge right here because we're looking at the right side of this thing. So we're looking at this direction in our right side view. And we're seeing two things really, or two things fighting for position. One is this corner or this edge right here. The other is the top of the hole. So you can see it up here in our top view, the hole is shown by these two hidden lines. In the right side view, we can see if we trace across here, well, here's the bottom. The top should be up here, but they didn't show it. And it's because you have a visible line fighting with a hidden line. In that case, the visible line wins. It's the most important. So that's the one you show. If we look at the last one, this is the one that always tricks people. On the last one at point C, they've shown a hidden line. Why would they do that? Well, here's what it is. If you look at this really closely, you might notice that in the very back, we have an edge right here that you can't see, but we know it's back there. So if you can imagine the edge in the back of this part that goes from here to here, that's occurring at this point, okay? And this is where people get in trouble, is they say, well, I've got a hole right here and then this edge way in the back, but this one's closer, so I'll show the center line for the hole. But it's not depth perception, it's not distance that makes the determining factor, it's line type. So even though the hole is closer, you're going to show the hidden line instead, because that's an actual feature that's on the part, unlike the imaginary line that goes through the middle of this circle. So hidden is more important than center. So remember, visible, hidden, center, we show the hidden line even though it's farther away. Okay. So at this point, I would urge you to take a short break. Obviously, this is video format, so you can keep going at whatever pace you want. But I'm going to take a quick break here and pause the video and get things kind of situated here. But what you want to do is you want to print out some of the sheets at this point from our module. So if you go into session 2, you're going to want to print out this guy. This has a bunch of different figures on it. This is the one called Orthographic Sketching Practice Drawings. We're going to not do all these. We'll do a couple of them, maybe 2 or 3 of them. So we're going to draw these. And then you're also going to want the blank sketching paper that looks like this. Now I'm going to do mine electronically here. But there's a sheet of paper that looks like this. That's what we're going to draw on top of. So each one of these drawings will go in one of these spots. Okay, so you're going to want to print that out also. That is the orthographic sketching blank paper. I've also put the answers in there for you, just kind of for kicks. But I wouldn't look at this until we get done. But you can compare yours to the answer key. That's the very top one that says practice solutions. So I did give you all the finished ones if you want to compare, just for comparison's sake. But we're going to look at how do you determine to draw these. I can give you the answer, obviously, but that doesn't help you. So we're going to look at how do you get from this to the finished drawing. Okay. So take a second and probably print those 2 or 3 sheets out. And then I'm going to go back and do them electronically on here to the best of my capabilities. Usually we draw these in class on the overhead projector, but we can't really do that. So I'm going to try this deal and see if I can draw it with my mouse. But you should do it with pencil and paper. That's going to be the easiest for you probably. So let's take a quick break here, and then when I come back in the video, we'll look at drawing some stuff. Okay, so let's see if we can draw some of these things orthographically. So we're going to start with the easiest one off the sheet that I gave you guys, which is number 1. So I'm going to see if I can zoom in on these a little bit here. All right, so here's the first one. And they've done a little bit of the work for us already in telling us which part of this thing is supposed to be the front view. So if you look right here, you can see the arrow is the front view. Now what we're going to do is kind of work our way around this thing. You want to look at what is the total width and total height and total depth of it. And we're going to put in all the visible lines, the hidden lines, and the center lines. So let's kind of work our way through this. Now ultimately, I want to show you just really quick what this is supposed to look like. So if you downloaded the answer key, you can see what it's supposed to look like. But I want to show you guys how you figure this out. So you can see we've got our front view, right view, and top view. So let's draw this. So what I do first is I look at what are the overall dimensions of this thing, and we're just going to count boxes in this. You know, eventually you'll use actual measurements, but for what we're doing, we're just going to count increments. So I'm going to cheat here and look at my printout instead of at my screen because it's kind of hard to see these blue lines. So if we look, we've got 8 boxes wide, 3 boxes deep, and our total height looks like 6. So I'm going to jump over to my grid paper, and what you want to do is kind of anchor each one of these views in the corners, and they should fit inside these boxes if you draw them correctly. So I'm going to use black for my visible lines, green for my hidden lines, or sorry, red for my hidden lines, and green for my center lines. All right, so starting out, we may need to do a little bit of erasing here, so I would recommend using pencil as you do this. But we're going to look, our total width is 8 boxes, so we're going to count over, we're going to start right here. So 1, 2, 3, 4, 5, 6, 7, 8, so we're going to end over here. We know our depth is 3 boxes, so our total depth is going to come back to here. Oh, sorry, I'm looking at this wrong. Our total height. So our width, our height we said is 1, 2, 3, 4, 5, 6 boxes. So I'm looking, when I do that, 1, 2, 3. I'm going to shift back to here, 4, 5, 6. So our total height is 6. So let's go up 6 boxes. 1, 2, 3, 4, 5, 6. Our total view will go right there. Let me get my eraser here and take out this dot I put in that's wrong. Okay, now we can see the base of this thing is 1.5 boxes tall, so it's going to come up to about here. And you can see I'm sort of just blocking this thing in, and then our middle 2 boxes are where this top part's going to go. So from there to there. So if I kind of sketch out and connect the dots here sort of, where all this stuff's going to end up. The bottom of the part's going to come across here. Hopefully you guys can draw this a little better than I can with my mouse. There's the top of the bottom section, which comes across. Then we're going to go straight up to here. This is taking all my concentration. There we go. Okay, now you can see that we also have another edge in here. Oh, I've screwed it up. I only went 5. This is really hard to do on the computer. Let me erase this. Do as I say, not as I do. So 1, 2, 3, 4, 5, 6. It should actually go up to here. There we go. Now, if we go back and look at this, you can see there's another edge that we're missing right now here. So we've drawn the total height in the back, which you can see, but this edge is, or this face is sort of laying away from us. So we need to draw in this edge right here also. So if we look at that, that's going to be 1, 2, 3.5 boxes up. So I'm going to go 1, 2, 3.5. Put a line across there. And I think at that point, that should cover our front view. So let's go to the right side view now. I'm going to give you guys a little trick here. I'm going to switch to sort of a light gray color. I'm going to do something called projecting lines. This tells you where the edges of your part are going to end up. So if I take this and sort of just project it across, you can use that to kind of mark the areas of interest on your drawing. And again, this is a lot easier with a pencil probably, so hopefully I can communicate this at least to you guys what we're trying to do here. So you notice I went through and I picked up anything that I cared about on there. So I know where the top and bottom of this go and the top and bottom of this section. Okay, so now what I'm going to do is I'm going to grab my other color. So I'm going to go back to my visible line color. And now we're looking at depth and height. The height information we already have. It's all noted by these gray lines. But we need to figure out the depth, which is 3 boxes. So I'm going to start right here in this corner. That's going to become my arbitrary start point. Okay. I'm going to go over 3 boxes, so 1, 2, 3 to right here. And I know the base goes up to here, so I'm going to go ahead and sort of trace out the area created by the gray lines and my points that I plotted. So that's the base in my right view. And then I know this thing is angled. So if I look at this, we're looking at it from this direction now. So the left side's going to go up a little bit, the right side's going to go up a lot, and then there's an angled line that connect them. So the easiest thing to do is find the sides first, and then the angled line will work itself out. So the nice thing is the height of these has already been determined. We're going to go to here and up to here. So I can go straight down, connect, straight down, connect, and again, these are supposed to be straight lines. So connect your endpoints. There we go. Okay, so there's my right side view. Now we're going to look at the top view, and I'm going to go back to projecting lines. So I'm going to switch back to my gray color. If you're using a pencil, you can leave these on your drawing. Just do a really light guide line, and then you leave them on there when you're done. So I'm going to come straight. Let's try that again. We can do better than that. Let's come straight down here. Actually, let's see if there's a line tool in here I can use. I'm not super familiar with this software. I just sort of downloaded it a minute ago so I can use it for you guys. It's got to have a line tool somewhere though. Alright, we'll just try this. That's not right. Now I've done it. Alright, we'll just do it the hard way. Alright, there's going to be one there, one there, and one there. Okay, so those are my guidelines. So remember, in my front view I've got height and width, in my right view I've got height and depth, and my top view I'm going to have width and depth. So all the information is technically on here. We just got to make it match. So I'm going to put an arbitrary start point kind of right here. Now remember, this thing is curved, so we're going to sort of plot out where this thing goes. I know that its depth is 3, so it's going to go from here to here in 3 boxes. It's also going to have these curves on the ends that are going to hit right here in the middle and over here. Now we need to look at these curves and figure out what the radius of them is. So if we look, the radius of these is going to be 1.5 units. So we know if I go over 1.5, the center point's going to be right here. 1.5, the center point's right here. So if I go straight up from that now, the curve is going to start here, come down, hit tangent, come down to here, and end right there. So if you can sort of block things in, it gives you kind of target points to hit. So I'm going to go ahead and do the straight sections of this thing. Here, and here. And now this will be the rough part. If I can curve this around with my mouse. Not too bad. And then I can fill in the circles here in the middle. So I know these circles are 1 unit. So the holes are going to go right here. Okay. And then lastly, if we look at this thing from the top down, we're going to have an edge here and an edge here. Now when you look at it from the top, you can't tell that it's sloped down, but we know that it is. So let's block that in and block that in. So now that's 1/3 of our drawing that's done, but really it's more than 1/3. It's probably honestly about 3/4 of it, because that's the hard part. Now what we do is we grab our other 2 colors, let's switch to red, and we're going to put in some hidden lines. Okay. So these are things that we know are there, but we can't see them. So really the only thing we have to worry about for this is the holes. So if we look, we know these holes go through the base, and I'm going to go straight down, and I know that they're going to go here and here, like the sides of the holes, and here and here. And I'm going to put in dashed lines for those. Okay, so remember our alphabet of lines. And I'll draw these out in just a second again, but these are dashed lines. Really hard to do on these tiny little sheets, so do the best you can. But our hidden lines look like this. A bunch of equally spaced dashes. Our visible lines should look like this. Just a solid line. And then our center lines that we're going to do last should be long, short, long. Okay, and that pattern repeats. But that's our alphabet of lines, okay? Visible, hidden, and center. So now we got the visible lines here. Let's go ahead and or sorry, we got the hidden lines here. Let's go over and do the hidden lines here. We know that same hole is going to go through the edge of this part on the right side. And then very last, we just have to put in the center lines. So anywhere we have a hole, we're going to do a center mark. The center mark looks like this. That goes in the hole, and then corresponding to that on the side, you have a center line. Okay, so I'm going to try my best to draw these things in. So there's a center mark, and luckily our CAD software, in a few weeks when we start doing this on a drawing page in CAD, it's a one button click and it automatically draws it on there. So there's my center mark. Down here I'm going to draw my center line. So long, short, long. And for the center lines, you want them to actually overhang a little bit. And that shows somebody that it's not a physical part of the object. It's actually just for visualization purposes. So start a little bit past your visible line, long, short, long. Long, that's that, I can do better than that. Long, short, long. There we go. That one's done. I think we've gotten it all. So a little messy, but it's not about how pretty it is at the end in this case. Hopefully yours looks better than mine, but it's about the process, the thought process as you go through and block in this drawing and create it all. Okay, so let's see if I zoom out a little bit here. And when I zoom out, it looks a little bit better even. So let's try another one. Let's jump down maybe to, which one do we want to try? Let's try number 2. We'll do one more. I want to leave a lot of these for you guys to look at as examples. And I think you can find this stuff in other resources as well, but I don't want you guys to have to sit and watch me draw these things forever. So let's do number 2 as another example. So if I zoom in here, get this set up, we'll switch back to our black color for visible lines. So we're looking at this one now. There we go. Okay, so I'm going to go ahead and figure out what's my overall size. So my front view is going to be right here. So we've got 1, 2, 3, 4, 5, 6, and our height is going to be 1, 2, 3, 4, 5, 6. This is 6 by 6. So let's go through and kind of block in this shape. And really, I don't know if I agree with their selection of a front view here. What they are calling the top view, I think I would probably use as my front view, but we're going to do what they told us to. So I'm going to start by going over 6. So 1, 2, 3, 4, 5, 6. Put a dot right here. We're going to go up 6 also. I think, if I counted that right. I don't think I did. Let's check that again. That should be 5. So if you count that again, the total height is 5, not 6. So 1, 2, 3, 4, 5. Go up to here. Now we're I like to just take it and kind of trace around. So if I start at that top corner, remember in the front view we can't see depth. Okay, so this is all going to look flat in that front view. We're going to come straight down. Then I'm going to go all the way over to the right side. Right there. I'm going to go up to there. I'm going to go back to the left 3 to where we get to that block, that cube that sits on the top, which is going to put me right here. And I know the corner of that is going to be up here. So I'm going to come straight over, straight up, and then straight over. Okay, so we're going to have some other edges in here also, but the thing you want to think about as you do this is when you draw that front face, imagine that the depth perception of everything, if you take it and shift it all to the same plane, you're drawing it all as if it's flat. You can't see the different depths and things until you look at the right view and the top view, but in the front view, all those different distances behind us, you're going to take those and bring them all forward and draw them in one flat plane. And that's what's kind of tricky about some of these. So if we look now, the edge right here, we're going to draw as this. So really we can see across the top of this thing, there's an edge that goes all the way across. Now it jogs around to different depths, but there is a physical edge all the way across the top of this part. So we're going to put that in right here. Right there. And then The only other thing we're going to see is some visual vertical lines right here. So we can see if we go over 2, we've got an edge. Go over one more box, we've got an edge. Another box, we have an edge. Another box, we have an edge. So basically, we're going to go over 2 lines, and then every box we're going to put a line because of all these individual things we've got going on. So let's go over 2 boxes. We've got an edge there, an edge here, an edge here, an edge here. Okay, we got all this stuff going on. I think that finishes our visible lines for that front view. So let's switch to our lighter color now. We're going to project some lines across. So I know here becomes the top. Here is the bottom. And then this is the top of the base section. Right there. Okay, so I'm going to switch back. And if I look at the right side of this thing, I know it's got a single edge across the back. So I'm going to go all the way down. There we go, all the way down. We're going to go over how many boxes here? 1, 2, 3, 4, 5. So we're going to go over 1, 2, 3, 4, 5 boxes to right there. We're going to go up 2, back to the right 2, then back up to the top and back to the beginning. Okay, so what I'm doing there is I'm visually, or in my mind, I'm tracing out, and I'm going straight down, then I'm going across the bottom, then up 2, over 2, up 2, back to the beginning. So you have to remember that everything is going to be flat in these views. Okay, there's no depth perception. Trace that out, trace that and that. There we go. Okay, now I'm going to go through and pick up those vertical lines so we can see we're going to have an edge across the bottom here where that cube is at. Then if I go over 2, I've got a notch right here that they've cut out. That little 1x1 notch that goes in the base. I can see the edges of that, and then the angled line that goes away from us right here. Okay, so we got that. Now we're going to jump up to the top view. So let's project our lines up. Anywhere you have an edge that you care about, we're going to have a lot of them here. So I'm just going to get the major ones, I think. Because I could technically bring all these up, but they don't really do much for us at that point. They just sort of get confusing. So I'm just going to bring up the major edges. All right, so now you want to map out kind of how big this part is. So our depth is 5, so I'm going to start here, go down 1, 2, 3, 4, 5, down to here. We're going to go over 6 boxes. 1, 2, 3, 4, 5, 6 over to here, which I guess I knew anyway because I projected my lines in there. So now let's kind of work our way around this thing. I know I've got this 3x3 cube that sits on the top, so I'm going to go ahead and fill that in. Okay, then the side of the part comes down to here. I'm going to go over 2 units. And now we're basically right here. So I'm going to go up 1 over 1. So up 1 and over 1 to right here. So I've got an angled line that goes through the middle of this. And I'm going to go over 1 box and then back down. And then kind of tracing out that other notch, I'm going to go over 1 and then to this corner right here, like that. Now I'm going to go up 1, draw out that little 1x1 notch that's on the right side, straight up, and then this part just continues over completely flat. Now the one thing we don't want to forget is there's a hole in this part, so I'm going to go to the top and draw that hole right in the middle of the 3x3 cube right there. So there are the visible lines for this thing. This one gets a little tricky. The good thing you guys will see later on as we do this is that in your CAD software you can basically drop these views on after you 3D model, and the computer will draw these views along with all the hidden lines and the visible lines. So we're going to do less and less of this as we go through the semester, but it's important that you understand what this language is and how to do it. And so I think drawing them with a pencil is the best way to start. So let's switch and finish this. Let's go to our red lines, which are the hidden lines. Thankfully, the only hidden lines we really have on here are due to this hole. So I'm going to go here, and this hole goes all the way down through the part. So I'm going to go here, and I'm going to have a hidden line that goes all the way down through for this hole. Same thing here, but remember, we're not going to overlap right here because the visible line is more important than the hidden line. So I'm going to start at the top, draw it down, and stop right there. We know the hole goes all the way through the part, but I'm not going to overlap that visible line. That visible line's too important. Same thing over here. I know that hole goes right here. I'm going to stop, and then here I can carry it all the way down through. Okay, switch to my center lines. I'm going to center mark my little hole on the top here as best I can, and then overhanging the visible line just a little bit. Long, short, long, short, long. Same thing over here. Long, short, long, short, long. And there we go. We're done. We've done another one. So if you want to practice some more of these, I did put the answer key in Ivy Learn for you guys. So that shows you kind of live how to do a couple of them. But if you go in here to the practice solutions, you guys can click on this and open it up. And here are the solutions for all of them. And the nice thing is these are drawn a little bit cleaner than my drawings I've been doing for you. So these are okay, but it's nice to see them perfectly drawn out in the solutions key. A lot of these I would say get pretty difficult too. Like, you know, if you get down to around, like maybe this one's especially bad. If you get down in here, if you can't see where every single line in here comes from, don't feel bad, especially if you're new to this. I would expect you guys maybe to be able to go through the first 4 or 5 without too many issues, maybe even 6, and see where everything's coming from. But I color-coded these lines so you can kind of match them up and see why things are the way they are. Now, this you do not need to finish. This is just for practice. So let's kind of break at this point and talk about what your assignment is for this session. So this page that we're working on here, this is just for practice. I gave you all the answers, okay? So let's go back to Ivy Learn and talk about what you guys need to do for your homework for session 2. There's a couple of things. So for session 2, my computer loads here. Okay, so we're going to go to your homework assignment. Close out all my extra windows here. And then let's go to lecture. Okay, so our lecture resources, if you look at the lecture resources, I have one more thing you guys are going to practice, which is a dice lab activity. What this is just a way for you to practice some really easy multi-view drawings really quickly. And what you're going to do is take this and just fill in the dots. You can print this out also, or if you just want to do it like in Microsoft Paint and upload it, you know, however you want to do it. I'm going to add a Dropbox to session 2 where you guys can upload that right here. So it'll say session 2 dice sketching lab activity. So all you're going to do, and I put these in session 2, if I can find it here in the lecture resources as, well, you know, actually, never mind, because I gave you the solutions in here. This can just be practice. We'll not do this as a homework assignment. So skip the dice thing. Go back and, you know, look at it, but I'm not going to require you to turn that in. So 2 things you need to turn in. Look at the dice lab just for reference, but 2 things you need to turn in. So the first is an online quiz, online assessment 2. You guys are going to do this. This one you get 1 chance on, so make sure you're happy with your answers on this one, okay? It's basically a quiz about some multi-view drawings, and it's going to give you a picture and then tell you to match it up. So for instance, this, which one of these views matches up what is shown on the arrowhead? Okay, and there's a lot of these, so I think there's 10 of them. But you're basically going to try and pick out which one matches up to the arrowhead. Okay, so that's the first part of your homework, and you get 1 try. So make sure you go through, take your time, slow down. That's going to be your quiz. Your homework, what you're going to do, if I go back to our module here, I've given you a similar but slightly easier set of orthographic sketches to do. So these are the ones you'll do for your homework. So same sketch paper, you're going to use the same blank sketching paper, but the homework handout is a little bit different. Okay, so these are easier. They're a lot more blocky. You guys are going to do all 9 of these for homework. So these are out of a textbook that I used to use for another class, and there's actually 2 pages of them. The second page is the one we did together, the harder ones. This is the first page, the ones that are a little bit easier. So I saved these for you so you can try them on your own. So you guys are going to draw these 1 through 9. You're going to do the front, right, and top view for each one. Okay. I would recommend using some like colored pencils if you can, or different colors of pens. So as you draw these, you can do different colors for different line types. It makes it a lot easier to figure out what's going on. So your homework assignment is 2 things. One is the online quiz. Pick out the correct view and submit your quiz when you're done. There's 10 of them. Your second thing is to draw 1 through 9 on the grid paper. So it'll look kind of like this when you get done. Now to turn it in, you have kind of 2 choices. You can scan it and upload it if you have a scanner, like a printer scanner. The other thing you can do is just take a picture of it with your phone. If it's a good like high-res picture that I can see, you can upload that to the Dropbox in Ivy Learn. There's also good apps you can get for your phone. I don't know if you have one or not already, but there are some good like scanning apps. Like I have one on my phone called Simple Scanner, where I can take a picture and it immediately turns it into a PDF file, and you can crop it and rotate it and stuff like that. So if you want to use your phone as a scanner, you can do that actually. Just look up a scanning app, and you can just take a picture and it turns it into a PDF instead of an image file. So draw these out by hand, pencil paper or pencil pen. When you're done, you're going to take a picture of it or scan it and upload that to the Dropbox in Ivy Learn. Okay. So, and again, the dice thing and the practice drawings that we did together, those are just for practice. I'm not going to grade those. So your only 2 graded assignments for this session are going to be the orthographic sketches 1 through 9. Do those on your own. I will turn the answers on like in a week when it's due, and then do the quiz online. Remember, you have a week to do both of these. So a week from whatever day this video activates. Okay. So that's all I got for you guys in this video. A lot of talk about orthographic drawings. Hopefully you learned something, and I think you'll learn some more by going through and practicing some more of these on your own. So good luck. If you have questions, shoot me an email. We might be able to do like a Zoom call maybe if absolutely necessary, or maybe later on in the week we'll do a Zoom call and kind of talk through some of these and see if we can get some answers figured out. But hopefully this is giving you enough of a leeway where you can feel like you can get some of these done on your own. So good luck, and I'll see you in the next video. Bye.